Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So just to introduce Max Jaderberg's work, as Yosha sort of said, when the organizers were looking at recommendations from the PC members and feedback from the community, internally, the way we're thinking about the oral talks especially was we wanted to identify the papers that we thought pretty much every deep learning researcher should know about. And so Max and his co-authors developed a, I want to say, remarkably simple end-to-end learning algorithm for learning a simple spatial transformation for the input layer or for other layers that gives remarkably good results. So we're excited to have him here today to tell us about that work. Do you want to take away? You ready, Max?
Okay, cool. Hi, my name is Max Jaderberg, and this is our work on spatial transformer networks, together with Karen, Andrew, and Corey at Google DeepMind. It's basically a new module for neural networks that adds some new, nice functionality for them. So we have convolutional networks, and convnets are awesome, and especially for vision, they really just cane everything. And part of what makes them really, really good is that you have these multiple layers of convolutions with max pooling, and having intertwining convolutions with max pooling gives you some sort of spatial invariance. But at the moment, this pooling is simplistic. You just take the max over a small window, and this window might be a little 2x2 segment. And this means that you only get very small amounts of invariance per pooling layer, and which means you can only be limited. You're only spatially invariant to a very limited amount of transformation. Also, another problem with max pooling at the moment is that you pull from across the entire input image. And yeah, obviously this is really, really effective, but the question is still, can we do better, or can we add some more functionality? And I think what I really thought we were missing is this conditional spatial warping. That is, conditional on your input image, can you allow your network to spatially warp and transform the data? And the reason why you might want to do that is that means your network can transform the data into a sort of normalized space, which is more expected by the subsequent layers of the network. Another nice thing about this, if you can do conditional spatial warping, is that you can then intelligently select features of interest, i.e. do attention, and so hopefully your networks can be invariant to more classes of spatial transformations. Obviously this isn't the first piece of work which wanted to do this. There's been a whole history of work which wanted to do, achieve spatial invariance, do pose normalization, having attention systems and detection systems. What I think is maybe something new that we bring to the table is this is quite a simple and efficient module which can be trained just from gradients, just with backprop. There's no extra supervision, and there's no reinforcement learning involved. So here's a preview of some results. Basically, this is a spatial transformer network trained to classify distorted MNIST digits. And here, for the purposes of video, I'm just smoothly varying the inputs. And you can see that automatically, just by minimizing classification error, these spatial transformer networks learn to attend to and pose normalize objects of interest. So there are three main parts of a spatial transformer. The first is this localization network, which takes an input feature map and gives you the transformation to be applied to that feature map. Then there's a grid generator, which produces a sampling grid. I use sampling in this sort of graphic sense here. And then there's a differentiable sampler, which applies that sampling grid and performs the transformation. So first is this localization network. This is just a mini network, maybe a two-layer fully connected network, which takes the input image or the input feature map and then regresses the parameters of the transformation to be applied to that feature map. So for an affine transformation, for example, these are the 6 elements of the affine matrix. Or if you're doing attention, then this would be 3 elements. This would be the scale, translation, x and y. You can also do thin plate spline, where you'd regress the control points, or something like that. So the next is the grid generator. The grid generator takes the transformation parameters from the localization network and produces this sampling grid. I don't have a cursor, but okay, the sampling grid is basically for each output pixel, the XY coordinates in the input where that output pixel gets its value from. And so here you can see an example for an affine transformation. To produce this transform sampling grid in green, you take a regular prior grid, this gray-black grid, which is just 1, 1, 1, 2, 1, 3 coordinates. And if you multiply the coordinates of that grid by this, you do matrix-matrix multiplication with the parameters regressed by your localization network, you get this transformed sampling grid in green. And then the third part of this framework is a differentiable sampler, and that takes the sampling grid and actually applies it to the input, producing the transformed output. And so if we just used the regular prior grid, this would be the identity transform, as you can see on the left, and you just get a complete pass-through of the image. But by applying the transformation on the sampling grid, you actually get a transformed image on the right. And so to do this resampling, you can do, for example, nearest neighbor resampling, or for most of the work I use bilinear interpolation. And so you can actually write image bilinear interpolation resampling out in this form, and if you write it out in this form, it's really easy to see how you can define gradients with respect to u, the input, and also, crucially, with respect to x and y, which are the coordinates of the individual sampling points in this sampling grid. And because we have all these gradients defined, this is a fully backproppable structure, and so we can actually backprop our classification error, for example, our global task loss, all the way through this structure. And so we can learn, we can train this localization net within our network just to minimize the global task loss without any extra supervision, no post-supervision, no localization supervision. And you can just drop this module into networks wherever you want, wherever makes sense. So you can have them straight after the input. You can have them deeper in the network, acting on convolutional feature maps rather than the image. You can have multiple transformers in parallel. The reason why you might want to do that is that would allow you to attend to or transform multiple objects in different ways in your data. Okay, so that's pretty much the crux of the technical stuff in the paper. Now it's just having fun with some transformed MNIST, some toy data. So here, the model is basically a spatial transformer acting on the input image, followed by a small classification network. And so we call this a spatial transformer network. And so this is the result of training this simple classification model on these distorted MNIST data sets. So here, for the purposes of a video, I'm just smoothly changing the input images. But this is trained on images. And so you can see this for different types of distortions of the data and also different types of transformations applied to the data. So, for example, we've got rotated MNIST on the top left with an affine transformation. And, for example, in the bottom right, you've got translated, rotated, and scaled MNIST with a thin plate spline transformation. And what you can see, the raw data is on the left, and you can see the transformation visualized on the input in the middle. And then the output of the transformer, which is fed to the remainder of the classifier, is always stable, pretty stable for all of these models, which means the classifier has a lot easier time to learn. And so here's some quantitative results. Basically, we just focus on this column, which is the rotation, translation, and scale distorted data. You can see that a fully connected network does pretty poorly. You get 5% error. This is because there's no mechanism for spatial invariance in a fully connected network. If you use a CNN with max pooling, well, you do really, really well. You get 0.8% error. What's interesting, though, is if you put a spatial transformer before a fully connected network, you recover the same performance as a CNN. So the spatial transformer is giving you that spatial invariance. And you can do even better by adding a spatial transformer before a CNN with max pooling as well, and so you get better again. And so you can have some fun with this framework, and to show you why you might want to have two transformers in parallel, here's a task where you have a two-channel input image, and in each channel of the image you've got a different digit which is randomly distorted in different ways. And here the model has two transformers in parallel, both transformers look at both input channels, but what happens during training is that one transformer specializes on one channel, the other on the other. So you can see the channel 1 output of spatial transformer 1 is stable while the channel 2 output isn't. Whereas for the other transformer, it's channel 2 which is stable, whereas the other isn't. So this makes it a lot easier for the subsequent fully connected network to classify and add up these two digits. And you can also do this unsupervised co-localization experiment, which is a bit like unsupervised tracking, where the goal here is to find the common object in this data set without actually saying what the object is. And so here you can set up the problem as a triplet loss using a transformer to find bounding boxes, and you want the distance in some embedding space to be small when you use a transformer, between two samples where you use a transformer, compared to if you just took a random bounding box. And on the bottom, you can kind of see the optimization process as it's happening. Okay, and so then we tried it on some real images, on Street View house numbers, which is this competitive computer vision data set. I basically took the state-of-the-art CNN architecture, and for example, for the last spatial transformer model, I just added 4 spatial transformers, one before each of the first 4 convolutional layers. So what's interesting about this model at the bottom is that the last spatial transformer actually acts on the convolutional feature maps, not the raw image. And if we use this, we get state-of-the-art results. And what's really interesting is that as we move from 64 pixels of background context to 128, we barely lose any performance. So, you know, these spatial transformers are doing what you want. They're actually attending to the objects of interest, and you can see this happening. It's actually progressively pose-normalizing the digits. And this just makes it easier for the remainder of the network to classify. We also tried this on fine-grained bird classification. So this is 200-way classification of different bird species. We started with some fine-tuned, some ImageNet pre-trained networks, and then fine-tuned them on birds. And the model that we used is this model where we have a single localization network which outputs multiple transformation parameters. So we have multiple transformers in parallel acting on the input image. The output of each of these transformers is then fed to its own inception architecture, whose features are concatenated and fed into a final 200-way linear classifier. And again, we get state-of-the-art results here, even though we have a very, very strong CNN baseline. And you can kind of see why this works on the, if you look at the first row of the images, this is the case where we have 2 transformers in parallel. We also do experiments with 4 transformers in parallel. But if you look at the 2 transformer images, you see the red transformer always focuses on the bird head, and the green transformer always focuses on the bird body. And that somehow pose normalizes this bird for the remaining classifier. And this is learnt just to minimize classification error. There's no extra supervision, there's no part annotation, there's no bounding boxes at all. And what's nice about this model is it allows you to use much higher resolution inputs and transform higher resolution inputs and then downsample them and still use your lower resolution classification architecture, so you can get better performance. And there's nothing really constraining us to just doing 2D transformations with this framework. You can extend this to, for example, 3D, where your third dimension is depth, or it could be time for a video. And it's pretty simple to do. And then you can do a 3D to 3D transformation. And something cool that you can do with this is actually, once you've done your 3D to 3D transformation, is then flatten the depth dimension by, for example, summing over it or doing a max operation over it. And this gives you a 2D output. But it's a projection of this 3D space. So you basically created this differentiable camera, where your network can now decide where to take a picture of this 3D input from. And so the nice thing about this, why you might want to do this, is that you can convert your 3D data problem from 3D, use this differentiable camera, project into 2D, and then use your nice, fast 2D convolutions to actually do classification. And so if we're going to do this, we need a 3D data set, and because we're addicted to MNIST, we're just going to take MNIST and then extrude it in 3 dimensions and create a voxelized MNIST. which we're then going to randomly place in various locations in this 3D space, very similar to like what we did in 2D. And so if we train a network to do classification on this data, these are the sort of results we get. On the left, you can see the raw input. Again, I'm just smoothly bouncing this digit through it. With the spatial transformation, the 3D to 3D transformation visualized in the raw input. In the middle is the output of the flattened output of the 3D transformer, the output of the differentiable camera, which is then fed into the classifier. So yeah, this kind of works. And yeah, I think that's all I've got time for. Here we've just created a differentiable spatial transformation mechanism, which adds new functionality to neural networks. It's a new building block for you to play with. It performs conditional spatial warping, which is learnt without any extra supervision, just by minimizing your global task loss. And there's some third-party open source implementations around, such as in Torch, Lasagna, and Cafe. And I'm sure there's probably more floating around, and they probably work because there's some new work which makes some nice use of them. So yeah, thanks.
Thanks. So we have time for a few questions. There are a couple mics at the back. People want to line up there. Hong Lak also has a mic and can run to people. Go for it.
Yes. Very interesting. I have been learning much during this week about attention, which I realize is a content addressable memory typically. Now what you're doing here is a coordinate addressed memory, much better for runtime, but often more difficult in terms of finding the right content. Do you feel that this is struggling to identify the right bit of data to extract?
In these cases, in these data sets that I've shown, it doesn't struggle at all, especially if you use a nice optimizer like Adam, for example. But you're right, if you have very big image and a very small object of interest, your signal from the gradients might not be enough to actually attend to that object, so it can be harder. Then you might need to resort to some reinforcement learning as well.
Makes sense. Thank you.
Very simple question. When you initialize, do you initialize based on a perturbation around just a standard identity transformation, or is it completely random Gaussian?
No. So we initialize, so the bias of the localization network gives you the identity transform, then with random weights. So it's basically the identity transform with a little bit of perturbation, as you said. Yeah.
Hi, fantastic work. I'm curious if you wanted to make the transformations even more stable under the sorts of animations you were showing earlier, what approach you might consider?
Yes, so all these animations, by the way, were just trained on single images. They weren't trained on movies. It was no recurrent net. It was just a feed-forward net. So, you know, if you want to start classifying video and stuff like that with a transformer, with an RNN, you can start putting smoothing costs, or you can start, I don't know. Yeah, if you had a model which was actually trained for this, it would be smoother, I would imagine.
Thank you.
Did you find the optimization to be easy or difficult? Did you use batch normalization or something?
For the birds experiment, we use batch normalization, and that definitely helps. In general, if you use Adam, the optimization is pretty straightforward. If you use SGD, you need to do a bit of gradient scaling on the localization network, because you effectively have, you might have 1,000 sample points, which all have gradients, sample point coordinates. And they all accumulate, for example, in the 6 parameters of the affine transformation. So there's this huge accumulation. So you just need to scale that if you use SGD. But yeah.
Maybe let's have Sergey start setting up. And maybe while the stairs are here. Well, Susan, one last question. Do you think, how broadly applicable do you think this is? Would you try it on audio data, for example?
Sorry. So I think this would work on, I mean, your data has to be smooth. That's kind of what you assume with this framework. So audio data would probably work. Any sort of smooth data, I think it would have a chance of working.
Thanks a lot. Let's thank Max again. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.